So we just talked a bunch about this material balance as an overview, and now I want to kind of get a little bit more detailed into this and delve into a couple of the processes here, and then determine a material balance for those processes. And those processes, we're going to focus on this reactor as one process. There we go. I'm going to call this R. This will be a distillation column, will be one of our processes. So I'll call it the distillation column. And then this azeotropic distillation will be our AZ process. And so we're not going to worry about what happens inside the actual tanks themselves. We're going to think of these as three boxes again, and from there we're just going to go ahead and denote what is flowing in and what is flowing out of each process, and then go ahead and solve for all of the different materials. Now, this will be quite a bit more difficult than the 4 flows we had going on in the last one, as now we have, I believe, what will end up being 34 different equations here by the end of this. However, we're going to write this all in vector format, so that will make it quite a bit easier to deal with. Now, alkene flow, we have kind of the same constraints for that going in immediately, so I'm just going to go ahead and we need to worry about the components for each stream that we find. I'm going to name each stream here on this diagram to make it a little bit easier to code later. And then I am also going, and we will go ahead and code in that way. I'll show you the prompt in just a moment, however, let's deal with the diagram here first. So this is the alkene stream in, and that stream in has associated with it, we'll just call this alkene Y, and it has all of its components associated with it. So that will be 4 different components. I'm just going to actually put a C here for components, and we know that there's 4 components. So we're trying to determine how many variables we're going to have right now. Awesome. So we have C components going in there, and then for the water stream, so we also have our water feed here, which is going to have C components into the distillation column there. Now we have this stream coming out of the reactor here, and that will have C components associated with it. Let's actually, I'm just going to simplify this arrow to here, C components, and we'll call this feed the distillation feed here. Okay, then from there we have another feed. We could call this the azeotropic feed, or we could call it D1 tops. We'll just see what happens there. And then I also have this feed down here, which is D1 bottom. And that's going back into this water recycle up there. Okay, and then for the azeotropic, we have an ether stream coming out here. So this is going to be C components associated with that. We have this alcohol stream that has C components, and then we have this water recycle. So we'll call this decanter water, and that has C components. So let's play. How many times did I write down C? 1, 2, 3, 4, 5, 6, 7, and yes, so I have 7 C's here, and 1, 2, 3, 4, 5, 6, 7, and I missed, oh, I didn't put a C down here with this guy, so that should be 8. So I have 8 C's, that's a highlighter, 8 C's, which will be 32 different variables. And then I also have 2 variables associated with the reactor in here, so 2 variables in here, and this is due to the fact that we have two reactions taking place, right? We have reaction 1 and reaction 2 if you watched my last video, which I'll go ahead and write here. Reaction 1 was this guy with water was becoming isopropanol, and reaction 2 was we had 2 isopropanol reacting to form water and a diethyl ether. There we are. So, those are the two variables associated with that reaction. Okay, so from here, let's go ahead and discuss how many equations are actually taking place here. So, I'll go ahead and put equations on this side. Now, for equations, we need to figure out what are our material balances. We have how many equations associated with each unit operation. The unit operations corresponding to these 3 processes here. We have 4 reactor equations, and then we have 4 equations for the distillation column, and then we should also have 4 equations associated with the azeotropic distillation. And then finally, we are going to have 4 equations associated with the vapor-liquid equilibrium relationships or chemical potential relationships. So all in all, that gives us 16 equations. Now we have 32 variables here from our C's, and then we need to add on our 2 reactor variables, which gives us a total of 34 variables. If we have 34 variables, and we have 16 equations with which to solve them, that gives us 18 variables left over, which means we need 18 specifications. Now, luckily, I do believe that we are given 18 specifications within our statement here. We just kind of have to sort through it and actually find them. So we did 3 unit operations to set up the material balance equations. And we are told that we have a combined molar flow of feed water and recycle streams 12 times that of the alkene molar flow rate. So that means that the water flow rate is equal to the alkene flow rate times 12. So that's going to be a constraint on our process here. We have decanter water mole fractions, and we have our distillate water mole fractions, as well as the same feed and product specifications as in part B. So we want to know molar flows and compositions of the feed, the bottoms, and the distillate of the column, as well as reaction extents and the flows of the ether and alcohol product streams. So basically we want to solve for the entire distillation column as far as what's flowing into it and the compositions of those, as well as the products leaving the final azeotropic distillation column. Now, I think from here we can go ahead, I'll go ahead and set up a little bit of the equations right here, and then you're going to see that they basically all follow each other, and from there we can go into Python and actually code it out. So, we have our 3 unit operations. Let's start with the reactor. again, we want to do output minus input minus reactions, right? So we want to do feed to the reactor minus the reactions minus the products, where reactions will be defined by, well, let's start with feed. Feed will be defined by flow rates multiplied by components. So that's going to be our feed there. Reactions will be our stoichiometries multiplied by our reaction extents. So that's our reactions. And then our products will be our flow rates again, multiplied by our components. Now, this product stream is, again, remember, it is the feed into this next column here. So this product stream can be also called D1F. And speaking of which, let's go ahead and talk about the distillation column here. Again, our feed, we have no reactions taking place in distillation columns, right? So we'll do D1F minus our products, which will go ahead and be two different, we have two different pipes kind of leaving here. We have the bottoms and we have the tops. So minus D1 tops minus D1 bottoms. And all of those are going to be, of course, I'm taking into account their flow rates there as well. And then for the azeotropic column, it would be virtually the same thing. The D1 tops is going to be the feed for that, and then we would subtract its products, which are the ether and the alcohol streams. And I'm not going to go ahead and write that down because I think that's fairly intuitive at this point. So the only other thing that I think is left to mention here is we are also given this specification right here, and we're told that is the mole fraction ratio between the distillate and the bottoms of the distillation column. The distillate being the top of the column, the D1 top, and the bottom. So those are the mole fraction ratios. That corresponds to kind of our chemical potential equations there, or our vapor-liquid equilibrium equations. I'll write that as VLE. And what that is basically we are told we are told this value here. Let's go ahead and call that array D constant, DC. And we just need to go ahead and to zero that out, we will just take the flow rate of the top, which would be D1 top Y over D1 bottom, I guess X, I think that would be a liquid because it's being distilled, and then you would subtract from that D1 constant array, and that's going to give us our last set of equations there. Remember, each one of these equations that I'm writing is technically in vector format, so it's really 4 equations due to the 4 components there. So that's going to go ahead and correspond to all of the equations that we need to go ahead and set up. And at this point, I think we can go ahead and transfer over to Colab and write out these equations here. So here we are again in Colab, and first we're going to go ahead and do our imports. I will go ahead as a notebook, absolutely not. Our numpy, of course, from scipy.optimize, import our root solver, and then finally we are going to import some different things this time. And this is going to be our JAX library here. Let's hope I that right, and maybe Jack's dot numpy. Try that. Jack's dot numpy maybe. Jack's dot numpy potentially. Let's just stop it. I know I messed it up. Stop. Let's try that. See if that's right. Okay, it is. Alright, so from here we could choose to define our equations or our variables first. I'm going to go ahead and start with all of our variables as I did in this last time here. So let me go ahead and pull up my variables again. Okay. So all that I want to do is start typing in our variables. Now, I could go ahead and copy this in from the last notebook, however, I'll just go ahead and write it back in to remind us anyway. We want to go ahead and make a dot dictionary here. And in this dictionary, we are going to go ahead and start with our feeds, which we know. So alkene, Y, and we will make that, let's see, I'm going to have to go and check that old note here for what it was. Yes, okay, so it was pure alkene. And then we have, let's go ahead and put our flow rate in here at 100, and then our water mole fraction. Oh, we need to go ahead and make these NP dot arrays, which means they need parentheses around that. So there's our arrays, and then we said this was pure water as well, and that's our input feeds into our first reactor. Now from here, let's actually go out and code our reactor feeds. Now, we were told that we had a constraint here, and this constraint was, if I go ahead and pull this up, we were told that the constraint was the combined molar flow of feed water and recycle water would be 12 times that of the alkene molar flow rate. So let's just call this our water to alkene ratio here, and that will be 12. Now, that constraint will come in handy in a couple of instances as far as creating some initial guesses and some bounds for us in our range variables in just a moment. Now from here we could go ahead, I'm just going to go ahead and do this sequentially and start filling out all of the different streams here. The first will be the, let me go ahead and put E dot there and run that once so that the E goes away. E equals, let's try that. Okay, well, it'll go ahead and be slow, so I may as well just keep writing here. So we went ahead and defined our ratio. What we need to go ahead and define next is going to be our I called it our D1 feed on the iPad there. And it is going to also be the products of the reaction, right? So I guess we could go ahead and put our, let's go call this reactor feed. We'll call this reactor constraint. Okay. Did it run? I don't know what's happening. Okay. Reactor constraint. And then here, we'll go ahead and call this distillation column. So we need to go ahead and put this in our D1 feed flow, and what that's going to go ahead and be for us is it's going to be a range, right? Range is anything we do not know, and what we can say is it will go ahead and be a range of, we need to provide some sort of initial guess as well as some bounds. Now, for this feed, what we need to go ahead and do is, let's see, we want to make it bounded from 0 to, let's say 2 times our ratio here. So 2 times W, our water to alkene ratio. And then we can just make our initial guess, 1 of our 2 times E dot water to alkene ratio. And then we can just make this the water to alkene ratio here. And I think that should work. Similarly, let's go ahead and do our D1 top here as another range. And for that, and let's just go ahead and say that we can make this, let's make our initial guesses an equal split of this ratio here. So 0, and then we would say the max would be if everything of our feed went into here, which would be maximized there. Okay. Similarly, basically the exact same thing can be the case for the bottoms. It's some sort of range there as well. Now we need to provide, we provided all of the, that would go ahead and be our, that would be our flow rates, as long as we go ahead and multiply by, let's see, alkene flow rate. I think I just called it, alkene flow rate there. There we are. Or I guess rather E dot alkene flow rate. And then we can just go ahead and copy this in here, like so. Multiply. Okay. So that will be the flow rates for each one of those streams that are associated with the distillation column. What we need to do now is provide some sort of guess for the compositions of that column, and for that I'm just going to use the comp function here. So I'll say D1 Fx, and I'll just say comp, and we just need to provide some sort of list here as an initial guess. So I'm just going to say 0.01 for the alkene, 0.03 for the ether, 0.06 for the alcohol, and 0.9 for the water. Remember, the water is going to be kind of the main component within this system. And we need to do the same for both the top and the bottom here. So we can say D1 top X and say comp, let's say 0.01, 0.33, 0.33, 0.33. Okay. And then finally we need to go ahead and do that for this bottom here. So D1 bottom is going to be a comp of, let's say, 0.001, 0.01, there's not going to be much ether there, 0.09 and 0.9, something like that. Or even let's give it a little bit more of each of these. There we go. Okay, let's try that. And so that gives us all of our variables associated with the distillation column, and I believe that is almost all of the unknowns associated with the entire system here. However, the other two unknowns that we have are going to be the molar flow rates as well as the extents of the reaction. And speaking of the reaction, I'm just now realizing that I forgot to go ahead and put that in there. Go ahead and run this again. Anyway, so let's go ahead and put the reaction equations in here. So we need to make a stoich of our reaction 1, and that is going to be equal to an array here of alkene first is going to be -1, and then we have next is our ether, and then alcohol, and then water. Same thing, let's do stoich of reaction 2, which is going to be another array here. This one being nothing to do with propylene, 1 ether, -2 alcohols, and 1 water. So there's our stoichs. We also need to do our reaction extents. We can go ahead and make these reaction extents the exact same as the reaction extents that we used in the last video. So we made these reaction extents, I believe it was, the first one we said could go, we gave it an initial guess of 50, and then we said it could go from 0 to 100, I believe. Yeah, something like that. And then for the second one, I believe we said we thought it was less common, potentially, which means that we want it to go, we gave it an initial guess of 25, and we said it could go from 0 to 50. And so those are all of our reaction equations. And now we need to mess with our azeotropic distillation column here. With this, we've already given it a feed, being the D1 tops, and so we need to go ahead and then mess with the output streams, which is going to be first the decanter water, which is, let's see here, we were given the mole fractions of that in our conditions. To be as such. And then we were also told to find the molar flow rates of the 2 output streams of ether and alcohol. I believe we measured in the last video, or we were given rather, their components. Yes, we were. So ether components were we are, and then the ether flow rate we said would be a range variable. Its initial guess we said was going to be 5, and then we said it would go from 0 to 50. For the alcohol moles, we said that the molar fractions were as follows. And then we said that our guess, alcohol, flow rate, we said was a range variable that could go from 50, and then it could go from 0 to 100. Okay, so now 2, 3, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay, so now we have all 18, yes. So now we have written down all of our specifications there. I think this is going to say failed again. Give me just a moment. Alright, apologies there. I just had to reformulate all of the running for all of that. And I didn't want to fix that on screen here. So I've ran all of my variables at this point, and I think we are now ready to move on to defining our equations. Although, I think I'm missing a couple here. Let me think. So I counted 18. Yes. So we are missing. Yes, I didn't put in our given as far as what D1C was, which was our constants. We said that was, let's see, an array here, and we were given that to be 100, 10, 5, and 0.2. There we go. And then we also missed, yeah, I think we missed the decanter water flow rate. Water flow rate. Add some unknown as well. We can just make this a range variable again, and then say water to a ratio 0 to 2 times water to a ratio. There we are. Okay. There we are. Perfect. Now I think we've defined everything appropriately. So these equations here, and I'm going to input some dictionary. Don't run that. Okay. So I'm going to input some dictionary. And now we just need to write down all of the equations we came up with before. We said, so let's start with the reactor. So I'm just going to call this reactor in all caps, and that's going to be equal to reactor feed minus reaction minus reactor product. Now, let's go ahead and define reactor feed first. Stop running. Reactor feed, we said, was going to be equal to our alkene feed multiplied by our alkene moles. Add that to our water. Let's see, our water is, okay, there's that error. Our water is, okay, water, let's see. Water, and did we never defined a flow rate for our water, so we'll have to do that in just a moment. Water flow rate multiplied by water mole fraction, which was X, yes. Add to that, we want to add the other things that come into our reactor tank is going to be our water recycle, which is equal to our D1 bottoms multiplied by their mole fraction. And then add to that our decanter water and multiply that by flow rate of the decanter water. Okay, and I need to go ahead and d-dot all of these. Okay, so that should be our reactor feed. Now we need to do our reactions. And this is going to look, I believe, exactly the same as our last video. It's going to be the extent of, let me actually copy these. Extent reaction 1 multiplied by stoic reaction 1 add that to stoic reaction 2 multiplied by the extent of reaction 2 there. And d dot that. Perfect. Then we need to go ahead and do our products. Our products, again, are going to be what's fed into this distillation column. So it will be our D1F multiplied, well, did I call it F? Yes, I did. Multiplied by D dot D1FX. Perfect. So that's our reactor products. So reactor products there. And then there's our reactor energy balance, or rather material balance. We're not messing with energy. So there we are, reactor, and we've done one of 3 of our unit processes there. So let's go ahead and do our distillation next, and that's again going to be equal to the feed minus the tops minus the bottoms. Now, there's no reaction taking place in the distillation column, which makes this a little bit easier. So let's say feed is, actually let's call this defeed, that way, d-top, actually, yeah. Okay, so defeed is going to be equal to, well, our distillation feed, so it's going to be equal to our reactor products right here. Now, is that a bit redundant? Couldn't I have just put RP right here and it'd been fine? Absolutely. But if we wanted to change just something or add some sort of pipe that was altering the feed of the distillation column, it's a little bit nicer to code it that way. That way, when we simulate it, it would be a little bit better. So tops next. Tops is going to be equal to our D1T multiplied by D1TF. Is that what I called it? Nope, D1TX. I couldn't remember which one was the feed and which one was the mole fraction. So D dot those, D1T, D1TX. Awesome. And then bottoms is going to be equal to D dot D1B multiplied by D dot D1BX. And yes, that's the bottoms there. So that's our distillation. Again, what we want to return is our reactor, our distillation, and azeotropic, and as well as we want to go ahead, actually this is going to be a jnp.concatenate there. And we want to do our VLEs as well, VLE, our vapor-liquid equilibria, as well as we are going to do our constraint here, I believe was the last one, yeah. So let's see. Let's go ahead and put our constraint in here. I'll just go ahead and call this constraint. Actually, I should make it in all caps because it's going to be one of our returns. Constraint. And what we're going to make that equal to is basically we're going to subtract what our actual constraint is, which will be water to alkene ratio. And what our actual water to alkene ratio is would be the ratio of our flow rates, right? So we're just going to go ahead and zero out our constraint here. So this would be all of the water recycle as well as the water flow rate. So d dot water flow rate plus d dot d1 bottoms plus d dot decanter water flow rate. For some reason I changed that one up. Yes. And then divide that by alkene flow rate there. That should be a d dot. There we go. So we want to return that constraint as well. Using a bracket, there we are. Okay, so now we need to go ahead and define our vapor-liquid equilibrium, which is, again, related directly to that constraint we were given up above. So vapor-liquid equilibrium is going to be equal to, let's see, it's going to be our tops over our bottoms, I believe, right? Mole fractions between the distillate and the bottoms. Yes, so D1 tops and mole fraction ratios, yes, I believe over the bottoms here, D dot D1 bottoms, X, and from that we will subtract our constant, which I called D1C constant. Okay. Wonderful. From here we need to go ahead and do our azeotropic, which will again be equal to, well, we'll just go ahead and code this out within here so it's less chunky. D1 tops, so I'll just call this tops, and then subtract the decanter water flow rate multiplied by the decanter water mole fraction, and then as well as our ether stream times its flow rate, F, minus the alcohol stream multiplied by its flow rate. Okay, and that should be all of our equations in there. Beautiful. And so now we're at the point where we can basically just go ahead and do exactly the same kind of stepwise logic that we did for the last one. The only difference here is that we're going to use JNP instead of NP due to the amount of variables that we are using. Okay, I just realized one error here. JNP dot at least one deep for this constraint. Reason being, we're concatenating arrays, and that's going to need to go ahead and be an at least one deep array. Okay, so from here, we need to go ahead and return our x0, x2, and t, our wrap function, and our x2 unknown, and our const. And that's going to be our, those are what we break up our, let's see, we called this our dictionary to named tuple here for our dictionary E. And let's hope that works. Perfect. From here then, all we can go ahead and do is, let's see, we just want to wrap our equations again, I believe. Yeah, wrap equations. And I think that's all we have to do for that. And we can say that that's equal to wrapped equations. Hopefully that works. Okay, cool. Alright, so now that we've gone ahead and done all of this, it is finally time to solve this entire thing. So solution is going to be equal to our root solver, and we're just going to pray this works right now. Okay, root solver, we want to find the root of our wrapped equations using x naught as our guess. Now, we have a method here that we're going to use in order to solve this, and Jacobian wrapped equations, I believe, is how it's performed. Let's see. Alright, that worked. And so now all we have to do, we can use this x2 unknown here of the solution. And then what we can do with that, it tells us what our unknowns are. We just want to go ahead and take the x values of this and then return it as a dictionary. I believe it's done like that. There we go. Again, if we wanted to see const of solution dot x dot underscore as dic. Okay, never mind. I don't really know how to do that part. But here are all of the unknowns. So you can see we've solved the two extents of the reactions here. Here we have the flow rate, the molar ratio, the top, its molar fraction, the bottom, its molar fraction, the decanter water flow rate, the ether flow rate, and the alcohol flow rate. And therefore we have solved every portion of this system, and that is as much material and energy balance as possible. So there we go. I appreciate you for sticking with me till the end here, and thanks for watching.